Maxwell's equations are a set of four fundamental equations in electromagnetism, named after the Scottish physicist James Clerk Maxwell, who formulated them in the 19th century. These equations describe the behavior of electric and magnetic fields and their interactions with electric charges and currents. They are a cornerstone of classical electrodynamics and have played a pivotal role in understanding and predicting a wide range of electromagnetic phenomena. Let's delve into each of Maxwell's equations. 1. Gauss's law for electricity. Gauss's law for electricity states that the electric flux through a closed surface is proportional to the total charge enclosed by that surface. Mathematically, it is represented as E equals 1/epsilon0 asterisk rho dV, where E is the electric field vector, d is a small vector element of the closed surface, epsilon0, epsilon naught, is the electric constant, permittivity of free space, denotes the surface integral, rho is the electric charge density, and represents the volume integral. In simpler terms, this equation tells us that the total electric flux out of a closed surface is equal to the total charge enclosed by that surface divided by epsilon0. 2. Gauss's law for magnetism. Gauss's law for magnetism states that the magnetic flux through a closed surface is always zero. In other words, there are no magnetic monopoles, isolated magnetic charges. Mathematically, it is represented as B equals 0, where B is the magnetic field vector, and d is a small vector element of the closed surface. This equation implies that magnetic field lines always form closed loops and that magnetic field lines never originate or terminate at isolated points, monopoles, as electric field lines do. 3. Faraday's law of electromagnetic induction. Faraday's law states that a changing magnetic field induces an electromotive force, EMF, or voltage around a closed loop. Mathematically, it is represented as EdL equals d beta/dt, where E is the electric field vector, dl is a small vector element of the closed loop, B is the magnetic field vector, and dt represents the change in time. This equation is the basis for understanding how electric generators and transformers work, where the relative motion between magnetic fields and conductors induces a flow of electric current. 4. Ampere's law with Maxwell's addition. Ampere's law states that the circulation of the magnetic field around a closed loop is proportional to the current passing through the loop. Maxwell's addition to Ampere's law introduces the concept of displacement current, which accounts for changing electric fields that behave similarly to electric currents. Mathematically, it is represented as B dl equals mu0 asterisk j d plus epsilon 0 asterisk d e d/dt, where B is the magnetic field vector, dl is a small vector element of the closed loop, mu0, mu naught, is the magnetic constant, permeability of free space, J is the electric current density, and epsilon 0 is the electric constant, permittivity of free space. The addition of the displacement current term, E/T, allows the equation to account for the production of magnetic fields due to changing electric fields. Maxwell's equations are essential in understanding the behavior of electromagnetic waves, the propagation of light, and the interactions between electromagnetic fields and matter. These equations form the foundation of classical electrodynamics and have had a profound impact on modern physics and technology, enabling the development of radio, television, wireless communication, and many other technologies that rely on the principles of electromagnetism.